In question 6, we have a series of reactions in order to predict the major organic products. So we start in question 6, part A, looking at Lindlar's catalyst. Lindlar's catalyst, we know, reduces alkynes to alkenes, and specifically to cis-alkenes. So we focus here on just the alkyne. The alkene, which is contained in the 6-membered ring, isn't reactive enough to react with Lindlar's catalyst, and so it'll remain untouched. But the alkyne gets reduced to the alkene. If stereochemistry was relevant in this problem, we would show it as the cis-alkene, but because the alkyne was terminal, there's no stereochemistry to indicate in the product. Part B is an Mcpba oxidation of an alkene, and if you recall, Mcpba oxidizes alkenes to give us epoxides. So the rest of our molecule remains untouched, and then the alkene turns into an epoxide. In this molecule, it's most likely that the epoxide would form on the opposite face of the two methyl groups based on steric considerations. Osmium tetroxide is a method for converting an alkene into a diol. And specifically, it gives us a cis-diol. So it doesn't matter whether we show both of these OH groups pointing up or both of them down, but we know they'll be on the same side. Part D gives us the reagents for the Simmons-Smith reaction. And in that reaction, we know our alkene is converted into a 3-membered ring. Part E, we're looking at ozonolysis. In an ozonolysis reaction, we get cleavage of the double bond completely, and we end up with carbonyls on both sides of where the alkene used to be. So in this case, this molecule will split into 2 completely separate molecules, both with carbonyls where the alkene was. Hydroboration, we know, gives us an anti-Markovnikov addition of an OH group. And that's true for whether we're dealing with an alkene or an alkyne. So we start this reaction out by converting the alkyne into an alcohol. But because we started with an alkyne here, the product we get, the alkene with the OH group on it, is an enol. Under basic conditions, enols will tautomerize pretty much completely to give the carbonyl. And so our final product here is the one containing the aldehyde. HBr, on the other hand, adds in a Markovnikov fashion. And it adds to alkenes, but not to other double bonds, so this carbon-oxygen double bond will remain untouched. In a Markovnikov addition, the hydrogen goes to the less substituted carbon, the other group goes to the more substituted carbon, and we can repeat that process for both alkenes. In part H, we have 2 steps here. The first is magnesium adds. It inserts itself between the carbon and the bromine to form a Grignard reagent, and the Grignard reagent does a substitution reaction onto the methyl iodide, and the overall result is that we get an aromatic ring containing a methyl group. In part I, we're attempting to add iodine to an alkene. And you may recall that when we talked about this reaction initially, we said that in general, iodine is not reactive enough to alkenes, and so we're very likely to get no reaction here. And finally, in part J, we're adding bromine. And Alright, in this molecule we have both an alkene and an alkyne, as well as an aromatic ring. Now the aromatic ring we don't have to worry about. It's not reactive enough to react with bromine, so it'll remain as is. The alkene can add bromines at each carbon, and then the alkyne can undergo the reaction twice, and so we end up with 2 bromines at each carbon.